So let's take the group SU2. Okay, so the SU2 group consists of 4x4 complex matrices. So U, not 4x4, 2x2. So these are 2x2 complex matrices, right? Which satisfy the following conditions. That it must be unitary, that if you take the U dagger, then it must be equal to U inverse. And if you take the determinant of U, then that must be equal to 1. This is how, these are the three conditions that define the SU2 group. Okay? Now, I'm going to claim that SU2 as a manifold is a three-sphere, or is an S3. Okay? So that means that the dimension of SU2 is 3. Okay, so we have shown this again and again, but I will repeat it, okay? So let's write U to be in terms of, alpha, beta, gamma, delta, where these are all complex numbers, okay? So alpha, beta, gamma, delta are complex numbers. And then if I use the condition that U dagger is equal to U inverse, then what happens is that I get alpha star, gamma star, beta star, delta star, okay? And here, what do I get? I get, I think, alpha. I forget what I get. Does anyone remember exactly the let me just dig up the.
Those elements should be swapped diagonals, and off diagonals would be negated.
Okay, yeah, Nahi, can you repeat? This should be, this is alpha,
you'll
right?
have delta. No, you'll have, I think, delta, and then alpha on like the 2-2 position.
This would be delta, right?
Yeah, and alpha on the 2-2 position, and no, 2-2 position actually.
Okay. Oh, I see. Yeah.
And then like minus gamma in the gamma position and minus beta in the beta position. And the determinant is 1, so you have no cofactor.
Yeah, okay, yeah. So there is no, yeah, because there's a divided by determinant, right? So this actually means that, so that the number of condition goes from 4 to 2, right? The number of parameters goes to 4 to 2. And then we can write U as alpha. Now beta is equal to minus beta squared, right? And gamma is equal to minus gamma squared, sorry, gamma star, right? And delta is equal to alpha star, right? Sorry, I should use beta here. So this is alpha, this is beta, and then, hang on, what is happening here? Yeah, okay. Why don't I do this? Why don't I substitute alpha, right? So then alpha becomes delta star, right? And this is delta. And then this is beta, and gamma becomes, is that right? Because we're supposed to have 2, right? Let me just look this up quickly, okay?
I think you need to transpose the other matrix. The one with the Hermitian conjugate. You didn't transpose it.
Yeah, you're right, exactly. Haha, thank you. Yeah. So this is gamma star, and this is, well, and I did, right? That's why beta, so alpha, oh yeah, this one's beta, this is gamma, right? I did transpose it, safe.
Oh, then you transpose the opposite one.
Oh, okay. So you're saying that this should be minus gamma, and this should be minus beta, right?
Yeah, yeah.
Okay, yeah. So yeah, so then I can keep alpha here, and I had beta here, but now instead I get minus gamma star, right? And where I had gamma, I keep gamma. And where I had delta, I have now alpha star. Okay, yeah, good. And then I also have to impose a condition that determinant of u is 1. Now, if I do this, then I get alpha squared minus, but that this minus cancels that minus, gamma squared equals to 1. But alpha is a complex number, so I can write it as, in terms of 2 real numbers, x1 plus I, x2. And gamma is also a complex number. I can write it as x3 plus I, x4. Okay, where all these xi's are real numbers, okay? So if I now rewrite this equation in terms of x's, I get x1 squared plus x2 squared plus x3 squared plus x4 squared is equals to 1. This is an equation for a 3-dimensional sphere, right? Because it's a constraint on 4. Yeah, and so it cuts down the number of independent parameters to 3. So does that convince you, Abdullah, that SU2 is a 3-dimensional manifold called S3?
Yes, sir.
Okay, good. So now, since SU2 is a unitary matrix, that means it's U. If I write U as, I can write e to the power I, 3 parameters. Let me call those theta A, TA. So there's a sum over A. A goes from 1 to 3. Okay, this is our formula for bridging. Let's write this as G. Okay. So since determinant of G must be 1, that means the trace of these matrices must be 0, right? These are equivalent statements. The other thing is that since G dagger is equal to G inverse, what is G dagger? It's E minus I theta A. Theta is a real number. So the dagger will be on the T. And this is equal to G inverse. G inverse is e to the power minus I theta A TA. Okay, so if you take the log of this and use the fact that all these the TAs are linearly independent, we get that TA dagger is equal to TA. So we get that TA dagger, that these are Hermitian generators, and that the traces are 0. In 2 by 2 dimensions, there are only 2 of these matrices. Sorry, 3 of these matrices, and they are proportional to the Pauli matrices. So we can choose our TAs to be the Pauli divided by 2. Okay, the factor of half is conventional, consistent with quantum mechanics. Okay, now using you can show that this, matrices satisfy this algebra. So this is the angular momentum algebra. So now, suppose there's a very beautiful formula, which is e to the power I theta a. If this is a Pauli sigma a by 2, then this is actually equal to, and you can prove this. This is part of your assignment, I think, that this is actually cosine of, how should I say this? Okay, yeah. I think the way to write this is, so this is easier to prove when there's only one of the parameters. So let's just take, but another way to show this is that if you have theta A is, say, theta 1, theta 2, and theta 3, then what you can do is that you can say, okay, okay, there is a direction you can. Right. What you can do is that you can represent it in terms of a vector, which is a unit vector. So the unit norm means that of these 3 parameters, only one is independent, and a direction. Oh, sorry. So a direction and an angle, theta. Yeah. Because to provide a direction, you need to, yeah, this is the direction vector. Okay, so let's call it, theta tilde, let's call it n tilde. And so this is essentially saying that, any combination of rotation can be thought of as one rotation around some axis. And there's a theorem by Euler that allows that to happen. So let's not, get bogged down in that. But the point is that you can write this in a very beautiful notation, where this is cosine of n. I think it's n dot theta, and then plus I think I'm not sure if it's, I think, yeah, it's n dot sigma. There could be a half or there couldn't be a half. I don't think there is a half. And then sine of n dot theta. Okay. So there could be some slight mistakes in expressing that. But what I'm trying to say is that there is an analog, a generalization of the Euler formula for the exponential of the Pauli matrices. So what, the details are not important. What's important is that given a point on your manifold S3, we get an element U, or let's call it G. We get a group element G in SU2 by this method. Okay? Abdullah, does that explain at a very sort of mechanical, operational level what's a what's the relationship between a Lie group and a Lie group element and a Lie algebra element? Sorry, I couldn't hear you.
Yes, sir.
Okay, any follow-up questions from this? Okay,
মানে এই দুইটার সাথে মানে আমরা মানে এই রিলেশনটা দেখাইতে চাচ্ছি কেন?
দেখাতে চাচ্ছি তার কারণ হচ্ছে কি we are, you asked the question, what is the relationship between a Lie group and Lie algebra, right? That was your question.
Yeah.
So a Lie group element is labeled by a point on a manifold. Okay, and that point on the manifold is given by, in this case, 3 numbers given here. Okay, so if I give you 3 numbers, these are 3 angles, right? There is no way a priority to turn that into a matrix. You want to turn that into a matrix, right? You want to turn that into, I'm just giving you the coordinates on a manifold, but you want to turn that into a matrix, which is part of the group, right? So do you think so that is the problem that we want to solve. Do you understand that?
Yes, sir.
So the way to solve it is that there's a bridge, which are the generators. Okay?
আরেকটা প্রশ্ন আছে মানে আমরা তো মানে গ্রুপ নিয়ে ইন্টারেস্টেড ছিলাম তো হঠাৎ করে মানে লি অ্যালজেব্রা নিয়ে ইন্টারেস্টেড হয়ে যাচ্ছে কেন মানে লি গ্রুপ থেকে লি algebra.
Yeah, that's a very good question. So what is Lie algebra? So if you have like a group, we have a group is some manifold, right? And on that manifold, there is some identity element 1. Suppose it's here. So what the Lie algebra is telling you is it's giving you the direction, the orthonormal direction around that identity element. And we want to find the representations of, so we want to find all the representations of a Lie group, right? So for example, we have SU2. SU2 হচ্ছে গিয়ে 2 by 2 matrices, right? But there could be a 10 by 10 representation of SU2, and there is. Okay, there could be a 10 by 10, there could be a 155 by 155 representation. Suppose you have a quantum mechanical system which has that many degrees of freedom somehow, and you're rotating it. So you'll have to find the appropriate matrix that acts on that system. So how do we do this? The way we do this is we first find the representations of the Lie algebra. Okay, we first find the representations of the Lie algebra. And once we have found the representation, suppose we already found a representation called the adjoint representation, right? Which I called FA. So once I find that representation, I can find the Lie group element by just using our formula to bridge. Okay, so if I find the representation of the Lie algebra, I get the representation of the Lie group. Okay, that's a very good question. But does it answer your question?
হ্যাঁ বুঝতে পারছি
Okay. Okay, who is next? I think Farhan came, it has a question, but other people had some questions before that. So
Okay, so I can wait.
yeah, just wait a second. Yeah. Okay. If there's no other question, then we can ask take
Uh,
Farhan.
sir?
Yeah.